Okay, so welcome back. We I'll talk about a few fun things to start with. So this is just a little video that came up. One of these visualizations. We like these visualizations. This should be. What is it? This is flight, just flight paths. The flight paths one. It's good fun. So let's watch that for a little bit. And so you put a disease on one of these, or a new religion. It's transported in. I mean, it's amazing. Now, of course, we're right at this moment in a situation where this is this fantastic visualization, but we don't know what happened to a particular plane. It's a terrible thing, right? Traveling from Malaysia to China. It's an extraordinary situation given how much we know about how much data we have coming in on how much instrumentation we put out in the real world, that we might actually lose a giant plane. It's a bad story, but it's, amidst everything else, it's surprising. It's strange. Fun to watch. Oh, yeah, we zoomed in on that. So we're going to talk about generating functions. We'll go back into that stuff and try to understand that. I have a little piece about random networks that I should tell you about. How to build them. Just it's a little aside piece, really. It's important. And then we'll go on to contagion, right? So we'll talk about contagion in talks, which is why the acronym works. And we're going to talk about it, in this really nice, clean way for random networks. It's a very basic kind of thing, spreading. Hey, right. And yeah, so it should be good. Contagion will take a while. Yeah, good stuff. Right. So that was fun. Okay. All right, I want to show you some other fun. So there's some paper, some work that I did years ago with my giant snowman. With, all right, you can see this okay, right? With a colleague, so we did our PhDs together. Josh White's, he was in physics, I was in math. Of course, we're working in earth science because why would you stay in your own department? And he's now at Georgia Tech in biology. So we were working on this problem of how trees fit together in forests. So it's a power law story, right? So it turns out that approximately, tree diameters, right? So there's this idea of diameter at breast height. So you figure out what that is. There's a standard height, and you figure out where that is on you. So now you have it marked out on you. And you're out, you're a field ecologist type person, you go out and you measure trees, right? Because you know it's here or here, wherever it is you measure. The good thing about trees is they don't run away, right? So you can go back a couple of years later, and you can measure if your trees are bigger or if they've died or whatever, right? So it's a good thing to study. So there's this observation, rough observation, that if you look at the distribution of tree sizes, they fit some power law size distribution with a decaying exponent of d to the -2, which sort of fits with the idea that maybe if you multiply by the cross-sectional area of all these things, that there's sort of an equipartition, so in a sense, if you take all the small guys and add up all their cross-sections, you take all the big guys and add up all their cross-sections, they're about the same, right? It's not really, that's sort of this beguiling, that's not probably my one, but it's, this idea that it's all sort of balanced. Anyway, we were thinking about how you might make a very simple physical system that produces that, right? So it's a physics thing. So what we did was we imagined it was just a blank square to start with, and we threw down at some rate, and it turns out not to matter what that rate is at all. You can pulse up and down and all sorts of things. It can be fast, slow, it doesn't matter. And then they grow at some rate as well, and that could be dynamic, right? So it could be fast and then slow down and all sorts of things. So imagine we're seeding these trees, right? And they grow, and we had a simple rule that if they hit another tree at any point, they stop. They stop growing and they're stuck, right? So you make this thing that's eventually stuck. So this is a packing problem, which you guys have a little bit of. There's a little bit to think about there with hexagonal packing, with how you distribute facilities. For when you have a uniform population, right, for the whole distributed distribution of resources story that we looked at. Anyway, so you end up with of course you get a power law size distribution. It's not exactly the ones you see in the world. But it turned out that you could, so there's a bunch of things in there. So there's this ridiculous thing here where we went away from circles to all sorts of shapes, right? So we figured out what you can do with rectangles of arbitrary size. You let them grow, and you figure out when they hit another rectangle. So you have to solve these little problems. And then you put rectangles together and make crosses and all sorts of things. These are two squares to make a little stuff. So, all right, so we did all this, and it depends on the aspect ratio. You get a different scaling exponent. If the aspect, right? If they're long and thin, they pack in a different way. All right, so we called it packing limited growth. We thought it was a lot of fun. It's a nice bit of work. Anyway, so there's some work that's just appeared now. And so there's one guy's in Minnesota, another one's in Western Australia. And they've been doing, it's not a growing thing. They just say, I'm going to have a distribution of shapes. So I'm going to have a shape, and I'm going to have a distribution of sizes, and I want to fit it into a space. I just want to show you what these guys have done. So they don't have to touch each other. They just have an algorithm that says, I put the first one down, and then I look at the next one, and it's smaller a little bit, right? I'm going to randomly choose a place for it. If it doesn't fit, I'll randomly choose another place. And I keep going. Okay. So they started to fit these things together, right? So lots of different shapes. Now we have these. And of course, at different angles, so they figured that out. And then, so there's some stuff. And then they start to get to some more crazy, like crystalline structures. Things that, so now we're fitting together fractals, which is pretty funny. You can put them in different objects, 3D, right? So our thing actually worked for arbitrary dimensions. We solved the problem in arbitrary dimensions, which was pretty cool. But some beautiful work by my colleague Josh. And anyway, so now they're fitting things into spaces, which is pretty crazy. So it's 15,000 cubes, there's all sorts of things here. And then this sort of stuff. So this is pretty crazy because the rings will sometimes, the random placement will actually put the tori around through each other, which is kind of a cool achievement. Packing is a very, very huge, big problem, right? That's how you there's all kinds of packings, right? But how do you put your apples and your things into baskets and so on? There's that. For shipping, how do you pack things into schedules and all sorts of stuff? There's a 1D version there. So it goes on and on. This is like a window. They pack things into the picture out of the door. Oh my god. Yeah, there's a big version of that. That's pretty cool. This just appeared. So they really went berserk, and they in fact 3D printed the shape. It's going to be great. So, for you guys who are fans of fractals, you might like this. This is packing anything, buses, fish. Oh my god. What else we got? And that's the page. Yeah. Oh, and there's a video. There's all sorts of good stuff. Yeah. Oh yeah, this is good. There you go. Sierpinski gaskets. All right. There's a nice expedition for you guys. I think that's it. That one's in French. I don't know what's going on. Okay. All right. So so things keep adding here. We are generating functions, random networks, applications, a little bit of applications of random networks, and then contagion. The contagion is very rich, interesting, beautiful math problems, very real problems. And we know that pure random networks are silly things, but generalized random networks are quite useful. Okay, so we can do a lot with these. Okay, so let's get back to generating functions. I'm going to try and get rid of all of this. It's not there. Oops. I rebooted this machine so it might survive. All right, generating functions. Okay. So, right, looks like it's alive. So okay, let's go back to these results. We're going to have to get our brains into this again.
All right, let me just touch on this again. Is this okay? Right, so we're trying to figure out, all right, we've got a random network, arbitrary random network. It's a surprise. Arbitrary random network. Right, so arbitrary degree distribution. You can add things like assortativity, for example, where the nodes of similar degrees connected. Okay, but this is what we have here is a arbitrary random network with a fixed degree distribution. All right, so that's P of k, and then we had R of k, right? So R of k is this associated distribution. That's the probability. You jump on an edge, you run along in one direction, just choose one direction. You hit a node, it's probably that it has k other friends, which is important for spreading, right? That's an important thing to think about for spreading. Okay. Good. So those are local pieces, right? This is just about a node, P of k, how many friends it has. This is just about how many friends a node has if you reach it, other friends a node has if you reach it along one of its edges. So they're local pieces. And then we want to move out, we're trying to figure out what's the largest component in this network, right? A very basic question. We've got to this point where we understand there's a phase transition from simple random networks, right? So as you dial up through average degree, you get to networks that are that have this big giant blob in them. There's never two, there's one big giant blob. So we want the probability that if we jump on a node, that it is part of a component, a connected component of size n. Right? That includes n. So there's n minus 1. So this is now becomes a global piece, right? This is a potentially very non-local. And this is the probability. So pi sub 0 is the probability that it has no friends, for example. Should match up with p of 0. Rho of n then is allied to R of k. So we jump on an edge, we run along it. It's a probability that that node is part of a subcomponent of size n, right? Just looking out that way. So if we break off this connection, we run along it, forget about what's back here, and we look out here, we see n nodes in that component. So this was the picture that we started to establish, right? And we have a couple of, I know I'm going to go through these things again, but I think it's fair enough. Just so our brains get in the right space. So we have this is by itself, right? The probability that you have n nodes in your component, and this is the global piece. This is a local piece. This is the probability that you have k friends. So we put these guys together. We can compose them in a certain kind of way, and because of randomness, it all works out. So we should be able to get this guy from two steps, if you like, from an iterative step, I should say. So here's the node. That's the same node as this one we're thinking about here. Here's the probability that has k friends. And then this pi of n must work such that, right, this is big pi of n. If it has k friends, then n1, n2, n3, all of these nodes and these subcomponents, the number of these nodes has to add up to n minus 1. I guess there's too many n's, but no, that's right, yeah. n minus 1 plus 1 to give you this n, right? So n equals 1 plus the sum of all of these little guys. So because of random, you could say this about any network, that's fine. You could say this about any network. You could draw this picture for any network, but we can actually do some calculations for random networks. That's the extra piece here, all right. Right, this is just generally has to be true. I mean, it gets messier if you have, these guys have friends and connections between them, but we're thinking about pure branching structures. Right, so there's a similar kind of story for rho of n, right, which is probably you run along an edge and you get to a subcomponent of n nodes. You can expand that story to say, okay, here's rho of n. Well, the next level of detail for it is that you hit a node. First of all, you hit a node. That guy has k other friends, so here they are. That's the probability you sample from that. And then you add up all of those, n1 down to nk, add up all of those, plus 1, and that must be that has to equal n. So this guy has to be related to itself somehow through R of k, right? So it has to be related to itself through R of k is the thing that binds rows to other rows. whereas P of k binds the pi's, right, to rows. So that's an important thing, right? So row makes sense with rows. There's an iterative story for row to row. And then once you've solved that, then you can get the pi story.
So, are those components found by, visually, but are they also defined?
So this, you mean,
Order of those components.
yeah, so it's okay, so the components here are, you start at a node and then you travel out along every edge until you can't find, you go and mark out every node. That's it, right? So there may be another component over here if it doesn't have any connections that's separated. So a component means there's a path from every node to every other node within that component. It's undirected, so directed can be a little more complicated, but
Yeah, if you like to start on a node, then you come with different components, and you start from another node.
yeah, so what you would do is you say, here's your whole network. You just pick one node at random, and then you find, and we haven't talked about this, but there's breadth first search and depth first search, right? So you'd say, okay, let's look at all our friends. And then you look at the next layer, and maybe these guys are connected. You next the next layer and the next layer, and eventually that runs out. So you've labeled all of them, and say we call them cluster 1. So we could put a little label for all of those. This is a nice, you call them cluster 1. Then you just go to the next node in your big list of nodes that's not labeled yet, and you call it 2, and you find the component it's part of. So you can go through and iteratively label every one of them. But it doesn't matter if you started here or here or here or here. I mean, you might, it might be called component 7 or component 22.
It's because there's no way to get from anything with a 1 to a 2.
Right, you'll never do that, right? So if you started here, that's all right. You would eventually mark out all of these guys.
So do components count friends of friends too? Is it everyone is connected, or is it just one?
So everyone, right? So the first step is friends. The next one's friends of friends. Yeah. So, right. This one has 4 components.
So rows just kind
This
of
is 4 components, for example. This system has 4 components. Yeah. And from, the subcomponent idea is, let's say we start random networks, we're not going to have any of this, right? Clustering structure or triangles. So but the idea for the other one is, right? You look at, well, there's a subcomponent of 1, 2, 3, 4 nodes. Keep asking questions.
So then the subcomponents change depending on what.
Subcomponent, yeah. So, subcomponent is well defined for every. So let's imagine they're all branching networks. Okay, so I see what you're saying. Okay, so here's one component. It doesn't matter where you start. This will be a component. But for each node, so each node in here has so 1, 2, 3, 4, 5, 6, 7, 8, 9. Each node is part of a component of size 9, right? So it has a little in it. If it wants to check, it has a 9 next to it. But each edge has you can go either way, and if you go in this direction, you get 1 as the size of that subcomponent. If you go in this direction, you get a subcomponent of size 8, because it's a subcomponent of size 8, right? If you started here, this would be a subcomponent of size 2, particular kind of one. Yeah, so each edge has a component that it can see going out to, a subcomponent, sorry, that it sees. And it's very much a non-local thing. It's a non-local thing. These are all non-local.
And that's what that is, the subcomponent.
Yeah.
story.
Yeah, so this could, here's a little piece of it, right? So where this guy connects to someone who has 1, 2, 3, 4 other friends. So R4, that R there, 4 other friends. And then you think about, well, this friend, what's the chance that this guy is connected to a subcomponent of size, whatever. This is a subcomponent of, so in this case, subcomponent of size 1, subcomponent of size 1 from here. Right, so you go to here, and there's subcomponent of size 1, but this one's a 4 over here. So 4 plus 1 plus 1 plus 1 is 7. So you're what you're getting, and then a plus 1 gives you the 8, right? So you're getting ways of partitioning integers. Right, so it's a nice math kind of problem, right? So you have to think about partitioning. So if this one connects to, if we're talking about, next picture. All right, this is good, we have to figure this out. If we're saying n is 33, right? Then you have to do 2 steps. You have to say, well, what's the chance that it's connected to k friends, k other friends? So that could be, you have to think about this, right? So it could have zero other friends is not going to work, right? Because that means this is of size 1. So it has to have at least one other friend. It can't have, did I say 33? Yeah, so it can't have more than 32 other friends, because at the limit of 32, they all have to be nodes. They all have to be nodes of degree 1. So that's the only possibility. So there is 2 things you have to account for. One is the number of friends, and then how many different ways you can partition these things. Right. So if it's 32, then you have to put 1 in each bin. If it's 27, then there are different ways of. If you have 27 friends, there are different ways of breaking up 32. Right. So we're going to have to count that up. So it's a bit of a problematic counting problem. What do you think? Yeah. That is a good picture?
The one on the board, yeah.
Oh, okay.
Yeah.
This little guy?
I think it makes it a
Oh yeah, all right, yeah.
makes it a little
Good.
bit clearer than-
Let's put a circle around it. Put a little check. Okay. Take a photo of it. Okay, so that helps. Okay, yeah, fair enough. All right, has actual numbers on it. Yeah, good, right? All right, so is that okay? Yeah, good questions. Excellent questions. You guys are rampaging with questions. Okay, so we have, which is great. So we have generating functions with these funny things where we multiply. So it's for probabilities of a discrete quantity, right? So k equals 0, 1, 2, 3. And we multiply the probability k by x to the k, and we do that for all of them and sum them up, and we get a continuous function which somehow helps us, and that's insane. Okay. So we did this for, as I said, we can do it for anything. We did it for p of k and r of k, right? The probability of a node having k friends and probability of an arbitrary node at the end of an edge, random edge, having k other friends. So we can make the same ones for the number of nodes in a component and the number of nodes in a subcomponent. Right? So we're just going to say we'll build these. Okay. Right? So we take whatever our row ends and our pi ends, we attach all these x's, x to the ends, and sum them up. Okay. Okay. So we're trying to get to the largest component, and the sneaky thing is usually when we set x equal to 1, we've got the sum of all the probabilities. That was a very elementary part of these guys. So it should add to 1. Probabilities add up to 1. Well, actually, we're doing something a bit sneaky with these guys. We're not actually looking at all components. We're looking at the finite ones. If there's an infinite one, right, so which is sort of what we're after with the giant component, because we're thinking about infinite networks. I mean, of course, in practice, it works for very large ones. Usually sort of 10,000 nodes is fine, right, actually. We are thinking about only the finite ones. And the finite ones all have this nice property of being pure branching networks, right? There's no way in a finite subnetwork you'll get a little closed loop. So they're pure branching networks. So if we put 1 into here, we're summing up the probability of being in a component of size n. N is 1, 2, 3, but not up to infinity, right? Up to infinity, but not including sort of infinity. Okay. So they're finite components. So this is probably that you're in a finite component. So the size of the largest component, the fractional size of the largest component, is 1 minus the probability that you land on a node that is in a finite component. 1 minus that is the probability that you land on a node that's in an infinite component, which is equivalent to landing on a node that's part of an infinite component, which is equivalent to the size, right? The fractional size. Is that all right? No? Okay. Yes, no? All right. Let's give this a bash. All right, you stop it. All right. So, in general, if you want to solve these problems, you have to go through all of these, right? You have to find them all, sort of, in principle, although we really just kind of want this one, so we don't have to solve everything. Right. Okay. Okay. So these are these results. We talked about them a little bit, but they're a bit terrifying. So, okay. We're going to go through them again. All right. So, a couple of things. We're going to have random variables that could take on the values 0, 1, 2, 3, right? Infinity. These are going to be their probability distributions. This is probably that if you sample from the U distribution, you get K. This is probably you get K if you sample from V. And we'll have their generating functions as F of U and F of V. Okay. So I'll call these sneaky results. So the first one is we're going to construct another random variable, right? Yeah. It's much better than a lemma. Okay. So there are classic ones like adding two random variables together, right? Or multiplying them together, right? These are classic kinds of constructions. They happen a lot. This is a bit of an odd one. So we're going to randomly, and I know we talked about this, we're going to randomly sample from U. That'll give us some number, including 0 potentially. And then, depends on what U is. And then we'll sum up however many we get. All right? I know. So we talked about this with the die and all that sort of stuff. Getting our brains going again. Okay, so it turns out the generating functions have this connection, which is pretty simple and spectacular. I mean, this is not a super complicated looking thing. It's just a bit odd. But there's a beautiful composition that you get out, right? So the U is this variable, that's on the outside. So we have to have the generating function. We put the generating function for V inside the generating function for U, and that gives us the next one. Right, so the generating function is the sum of x, right? Something times x to the 0, something times x squared, blah, blah, blah. We're going to put a generating function inside each of those x's. We're going to replace each x, right? So x to the 17 will have an infinite series in it to the power of 17. That's pretty yucky, right? So it's going to look like you have this sort of thing. So you'll have your f of v of x to the k, right? U of k. Cool. All right, so let's see, how do we get that? Okay. I'm going to go through it. This is basically where we got to. All right, so w is this new variable. So what's the probability that w is k? Okay, so we do this two-step process. We sample from u, we get some number, 17, and then we sample from v 17 times, and we add them all together. What's probably that equals k? Which is pretty nice. All right. Okay, so let's think about it. So this should be okay. So it's the sum from j equals 0 to infinity times the probability that we get j, right, from u. So that's our first thing that we do. So that's a probability there. And then we multiply each one by probability that the sum of these j draws of the variable of v, right? So we're going to sample from v j times, that they sum up to k. That's what we want, right? We're trying to get k, and we have to do this two-step thing. What do you think? Okay. So let's start transforming this thing. So we're going to keep this piece here. This is pretty benign. There's nothing too nasty there. Well, what's the probability that we get, right, these are independent things. So if you have independent variables, the probability of, right, you have to multiply them together. So this is the notation we want, right? So, okay, so we can think of every partition I1, I2 up to ij, right? There are j integers. We have j integers such that when we add them together, we get k, because we're trying to get k. We have j ways of cutting the integer k up. And then we want the probability that the first one came out as I1, the next one came out as I2, the next, right, up to the last one coming out as ij. And that's multiply those two guys together, that's a probability that we got I1, I2, ij, and we needed it to sum to k. We haven't we've just got a restriction here. We haven't really sort of enforced it mathematically. We've just kind of said. So we're capturing all the possibilities. All right, okay. So that's just, this is w of k, right? This is w of k. So we want to make the generating function for w. So we stick our wk in and we can put an x to the k here and we sum over it. This is just the definition of the generating function. Okay? Okay. All right, so we've taken this whole blob and we've put it here. And now we've got a sum from k equals 0 to infinity at the front, right? And we have an x to the k on the end. Now, there's some things that we can do. So there's x to the k, right? So the whole point of this is that the sum of these i's have to equal k, because that's right. So we can write this as k equals I1 plus I2 plus I up to ij, just right. And then we could sprinkle them through. We could put one here, the x to the I1, and then the x to the I2 here. Okay. So let's see what we're doing. All right, so we're going to do some sneakiness here to start with. We'll put this sum outside, the uj. This is kind of getting us towards our finishing product, which is we want sum of something, whatever it is. So this is k equals 0 to uk times some blob to the k. We're trying to get to some blob to the k, and we want to see that that blob is the generating function for v. So we've manufactured that a little bit at the start, right? We've pulled this piece out, and now this is looking like the start of the generating function for u, right? And then we want some nasty thing to the power of j. Okay, so what's left? As I said, we can replace that k, because it's what by definition is what it is. It's a sum of these i's, and then sprinkle them through. That's what's happened, right? So we've reallocated things a little bit. This is still the same restriction. Okay. Now this is starting to look like a component of the generating function for v. Right? Generating function for v is made up of, I don't know, right? F of v, just quite simply, is vk, x to the k. Right? So it's got all these bits in it. vk, xk's. Right? Whatever it is. So in vi1, xi1. That is a little piece of it. Okay, so this is everything repeated from the last line. This is what you need to think about for a little while, right? So, well, you don't have to, but it's good to do this. That this is the xk piece of this quantity to the power of j, right? So this is this infinite sum. It's vi prime xi prime. If we raise that to a power of j, then right, so it's a sum, and it's going to appear j times, and we're going to multiply all the way through, right? And from each of these j elements in the product, we pick up one of the vi xi, right? So this is from the first Imagine this repeated j times. This one is from the first one. This one is from the second one. This is from the jth one. And you're allowed to pick from any of the guys in the first one, any of the guys in the second one, any of the guys in the next one. And as long as they add up to, if the ones you've picked are such that they end up with an x to the k power, then that's what we've got here. You can make yourself somewhat happier if you think about, just small examples. Something like 1 plus x1, 1 plus x2. And this is just a completely different thing. I mean, just think about how the cross terms appear, right? I'll give you another example. I don't know, maybe like this. 1 plus ax, 1 plus bx, 1 plus cx. Right, so the ones, you get 1 cubed, plus you get a plus b plus c, right? A plus b plus c times x. Right, and then all the cross terms, bc plus ac times x squared, and then you get plus abc x cubed. Right. So in getting this one, a plus b plus c, what's missing is there's a 1 squared and a 1 squared and a 1 squared, because it was a times 1 times 1, and then the next one is the 1 times the bx times the 1, and the next one is 1 times cx. You're picking out those pieces. So this is to the power of x0, 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 right? You're choosing things such that this is x to the 1, and this is x to the 0. All right, so you may have to think about that one. This thing is, in fact, of course, the generating function for v. So this is actually the generating function for v to the power of j. So we're there, basically, right? This was for here, right? It's this piece. This is the sum. Yeah. Right, the x to the k is included. There's a sum from k equals 0 to infinity, which makes it this guy. Yeah. All right. So this is a little horrific. There might be other ways to prove it that I haven't got into my head, but this is a fun way to do it. Okay, so charmingly simple result. But and for a fairly easily stated but kind of odd composition of two distributions, right? Two probability distributions. All right, bonus. The second one is it's not as sneaky as all, right? At all. So it's a much simpler thing. So if we have a random variable u, it has a distribution u sub k. If we add to it +1, right? So v is u plus 1. Then we just get this nice thing, right? So this new generating function is the old one times x. That's all, right? And so the reason is pretty simple. So v of k is simply equal to, so the probability that v, the sample v is equal to k, is probably that u is equal to k minus 1, right? Because we're just adding 1. Right? It's probably we get a 7 here, it's probably we get a 6 for this guy. That's it. Okay, and v0 is 0. There's no way we get that guy, right? Because these things are defined for positive 0, 1, 2, 3, 4. Okay, we can't get this. If I were defined on all integers, yes, of course. All right, so okay, so we can just put these things together. Then we have f of v, right? This is just the definition. We just put in uk minus 1, and we know v0 equals 0, so we can start at k equals 1. So we can just shift this index down. We'll start from j. We'll say j equals k minus 1, and we'll start from, right? So this will just be j. This is j equals 0. K equals j plus 1 then. So this is a j plus 1, and we can pull that one guy out. And this is just the generating function for u. So it's a shifting thing. If you take a generating function and shift it, multiply by x, it shifts how the it changes the index of the probability distribution. So you can, you have to be a little more thoughtful about it, but you could also divide by x or multiply by x squared. If you divide by x, you have to subtract some things off already. But all right, and so these guys are. Well, I guess in principle you do it. We're going to say u is 0 and above, but v could in fact, certainly take on negative numbers. So, yeah, so it's just x to the I. It's going to be x to the minus I if we have, yeah, fine. Is that okay? So it's just a little shift thing. We need the +1 because that's exactly this picture, right? We have a plus, when we did this one layer of iteration for rho of n and pi of n, we got a +1 popping up. All right, so let's see. Let's get it to work. Okay, good. So this is this picture again, right? So there's going to be a +1 in here. Here it is, +1. That's why we'll need it. We have to concentrate. All right, so you see how this is going to work. Hopefully this is going to be k samples. And we know how to compose the generating functions. We don't know how to... So let me just say, so we understand... for that first sneaky result, it's not obvious at all what the probability distribution will be, right? So W is this result of sampling U. So you sample from U, you get some number, and you sample from V, however many times that is, add them up. They might have very nicely well-defined probability distributions, but the new probability distribution is a mess, but its generating function is at least simply described, right? Generating function we can write down probably, but we might not be able to unpack it. So is that okay? This is one of these kind of funny things, like Fourier's like this as well. Horrible things might be happening in real space or with time. You transform into Fourier, nice things can happen, okay. All right. So let's see. So we're trying to get this guy. So we have pi of n, right? Again, it's probably that you land on a random node. It's probably that it has the size n. So this first level of iteration is, well, okay, let's say it has k friends. Right? It has k friends with probability k. And then we have to figure out what's the probability that the sum of all of these subcomponents coming out, right? All of these subcomponents sum up to n minus 1. That's the statement. They have to sum up to n minus 1. You've got a +1 in the middle. So that's exactly our two sneaky results, actually, right? So this is about probabilities. So we can see how the probabilities are trying to work. We can write down how their generating functions behave. So the generating function for pi is going to be two pieces. So the two pieces. One is the generating function for p, just the probability of the node has degree k, composed with the probability of the generating function for rho. Right? This is u and v. This is what we have for u and v, right? So this is how many samples, and then this is the size of the samples, the probability for the size of those samples. But we have to add 1 to get the right generating function, because this is the generating function for n minus 1 things. So we have to multiply by an x, and that shifts it to being the right generating function. Just a tiny little extra bit. So it doesn't matter how horrible these things are. We have a very simple statement about their generating functions, which makes us really happy. Yep.
Can you say one more time, f of capital P is?
I'd be thrilled to. So that's the generating function for P of k, which is the fundamental thing here. So that everything else stems from P of k, right? Because we're sitting here. We're gonna. Okay, so I'm gonna sample from this, and what's probably I'm in a component of size n, right? Jump on a node, and it just has an n written next to it, right? another way to do that sampling is there's no n there, but I know what I know these other two things. I know what P of k is, and I know what rho of n is. So I'm going to sample from a node, and what I get back is how many friends it has. And then I'm going to sample from this row thing, which is pretty crazy too, right? But that's the number of, if I run it along an edge, how big's that subcomponent? Which is this picture that,
So f of rho is the generating function for how big the next component.
the subcomponents are. Yeah. It's a generating function for rho of n. Rho of n is the probability that a subcomponent has size n. Yeah. I mean, it's just very strange. You do a horribly weird thing to something and it makes it beautifully simple, but hard to understand. Okay. So, there are two pieces. Yeah? Sort of. So this one is okay, but so all we know is this, right? We know P. That's what we turn up to the table with. We have P. But we don't know what these guys are. So this is not going to help. It's not enough, right? I mean, we're also solving for functions, which is pretty insane. Okay, that's a lot. Okay. Okay? Good. All right, so let's do this one, right? We need to solve this. That was one step, but it's really about edges. It's always about edges, right? You solve a lot of things by thinking about how things work on edges. Okay, so this is the original guy. So subcomponent of n nodes, and we use the underlying degree distribution to create the probability that a node has k other friends, right? They're very simply related. Right, it's k plus 1 times p of k plus 1 divided by the average degree. So we get that. And we say we can then connect rho of n to itself because, okay, rho of n, you're going to have one friend at least here, and then this guy has k other friends. All of these guys have to add up to be n minus 1. Okay, so same kind of story as we just had for pi. Let's write down, okay, lots of words, right? So a random link is leading to a finite subcomponent of size n. So it's a probability that you get to a node that leads to a set of subcomponents who in total have total size n minus 1. All right. Okay, fine. So that's going to be the sum over how many friends this one node could have, right? It could have k friends, and then probably the sum of all of those guys is equal to the subcomponents is n minus 1. So this looks again. This is just like this, right? This is u of k. This is p of. This is v of. Sorry, that's not right. This is exactly the same story as the sneaky result one. Okay, yeah, right. Okay, so the generating function for rho is going to be built out of itself in the following way. We have a generating function for r, right? Because that's the number of samples we're going to make, k. And then these are the things we're going to sample from. Rho is the thing we sample from. We add them together, so we're going to put that gets composed in there. And then we have to add one for the node that we hit. Right? This is the f of u, f of v composition. And again, it's because we hit a node, we know that it has k other friends, and this row of n is the probability that each of those guys has n friends, and we have to add them up. So now we have an equation that is at least this has you can start to think you can solve this one, right? So it's a recursive one. I mean, they're functions. It's a little bit nasty, but you want your function rows to be such that x. When you put it in here as a function of whatever the generating function is for r, whatever that is, and then multiplied by x, you get it back. Now, this is a sum of x. This is a sum of stuff times x, put in here with powers and things, and this is a sum of stuff times x. So, in principle, you can start to say, let's equate, things that the linear term and then the x squared terms and the x cubed. You could, in principle, march through it. And you give it to Wolfram Alpha, to Mathematica, and it spits back a giant page of madness. But you can do it, right? You can do it. So, and if you want to know what the probability of a component of being of size 1 and 2 and 3 and 4, so that's the thing. You have to actually march out slowly. You'd have to figure it out that way. You'd get the probability of a component, right? To get to 72 would take a little while, or 70 billion. Okay, so okay. I know. So, but we have these two cool equations now. So it's a bit of a battle, but they're surprisingly clean and small. Okay, but they are very inscrutable when you first come across. If you come across them like this, like someone says, blah blah blah, random networks. Obviously, this is true, which happens in papers. So I try to avoid that for you, even though everyone is sad now. Okay, so yeah. Okay, but they're pretty good. All right, so we have f of p is the binding piece here, f of rho is the binding piece here, and it really should feel the right way, right? This is about edges. This is the edge probability stuff, right? This is about nodes. This is node-centric. This is node-centric. So the node-centric one is gotten from a node-centric story here connecting into edges. Edge-centric, you have to use edges here, and it connects you into other edges. So this one we can undo, and then we can get to this guy. Okay. We know a bunch of things. So all right, so we have f of p and f of rho. We actually know f of r, right? This is something we derived early on, right? So it's the derivative of f of p divided by the derivative evaluated at 1. Okay, that was a step ago, but is okay? All right, so we know that, so that's good. And in principle, someone hands you p, so you've got the whole function. So we're gonna see if we can unwrap that guy first. As I said, we know this, we know all this, we don't know these things. And then once you've got f rho, you just stick it in here and it pulls f of pi out. Okay. Okay. Let's try and figure out what we're trying to do. So we're really interested in the big one. Okay. This is all about the finite components. So we're doing this funny dance where we ignore the thing we're trying to get to, but we understand everything else about all the rest of it, and then we say, okay, well, it's a negative space story. The thing you look at is too hard. You have to look at everything else, and you're like, oh, that's what. Yeah. All right. So we wanted this, right? S1 is 1 minus f of pi evaluated at 1, the generating function evaluated at 1. So we don't have to get to the probability. We don't have to unpack the probability distribution and put it all over the table and have a horrible mess and like reams of Mathematica. I want to spare you that. Okay, so we can just set x equals 1. Why not? All right, so we'll put x equals 1 in this thing. We had x's here, so they're gone. And so, okay, that's not so bad. So now this is actually this is some number, right? So this is actually, here's a function we in principle know. And this is a fixed point of that. Right, so we right? So so we know that 1 will work actually, right? So 1 works because that's the nature of not all generating functions, but proper generating functions, right? Is that they evaluate at 1, they give you 1 because that's the sum of the probabilities. So we kind of can see one answer there, yeah? 0 won't work if there's if f of 0 is non-zero. Sorry. Yeah, that's right. Yeah, and then once we've got it from here, we can just stick it in here, map it to this. Right. So you can do this numerically, right? Depending on your mess, and you plug it in, right? So that's a little bit better. It's a little bit better, right? We don't have to. We still have, in principle, this. It depends how nice this thing is, and of course, for some random networks, it's all very nice. All right, So this is an exercise that should be in your assignments. Standard random graphs, right? So let's go back to something that doesn't exist. And this is the form for these guys. Okay, this is the generating function for P, right? The fundamental part of a generalized random network has this very nice little form here. So you can figure this out, right? So it's a Poisson degree distribution. You stick your Poisson degree distribution in, multiply by x to the k, sum from k equals 0 to infinity, and you should get this little blob. So when x is 1, it's good. What happens when x equals 1? Does it do the right thing? When x equals 1, yeah, yeah. So it's e to the 0, so it's so it's 1. So that's good. But it's a continuous function. It's a funny looking little beast. Okay, so let's compute the generating function for r of k. Okay, all right. So we've got this definition. Take the derivative of this thing. So we're going to take this derivative and divide it by itself, evaluated at 1. Right, so what's the... I guess I was a little sneaky there. All right. Yeah. All right. There's probably a piece that I could have. Okay. Thing. Frame 33. All right, fine, doesn't matter. Okay, you differentiate this. This is you get the k will come down, right? So there'll be an average degree will appear there. An average degree. I mean, in principle, they have been cancelled, but it's okay. Average degree there, average degree there. So they cancel, and then we set x prime equal to 1 on the bottom. So this will be, right, like we had before. It's e to the 0. So this is just 1. So we just end up with this, which is f of p. So it's the same generating function, right? They are, in fact, the same probability distribution. We've talked about this a little bit before, right? So the probability distribution for, so P of k equals R of k. This is just for pure random networks. It's an odd thing. It means that your friends always have, on average, one more friend than you. But, which is horrible. If you live in a Poisson degree distribution world, it's worse probably in the real world, right? So, skewed distributions. So, but if you think about their other friends, that matches up with you. You being a randomly selected human being that you resample from. So, yeah. Okay, so this is funny though. It means that the right-hand sides of both of these equations that we just had, right, f of p and f of p, these are the same now for this particular kind of network. So these are the same. This is f of p. So f of rho equals f of p times f of rho, and f of pi is f of p times f of rho, right? So whatever we solve for here, we just put it in here, we have to get f of rho again, right? The right-hand sides are the same. So that's why there was that horrible little mistake that we made ages ago. That's why it works. Only for these things. It's a terrible, terrible trap. Okay. Pretty cool. So this is not even for x equals 1. This is in general. This is absolutely true. All right. So we're down to just this business. We just have one equation. And you know f of pi equals f of rho, so you can say that so everything's the same, right? So it's not so for these guys, r of k for Poisson, right, for pure random graphs, this is true as well. Pi of n equals rho of n. Right, so we're back down to just this thing. Cool. All right. And we know we have this generating function already, so it's x to the minus k. It's really this thing, 1 minus this blob in here. So in principle, that's how you would solve the whole thing for Poisson degree distribution. It's kind of nasty, right? So you have a sum here, you have a sum up in here, and then you have to start unpacking the thing and figuring out all of the prefactors, coefficients. All right. So we really wanted this. S1 is 1 minus f pi of 1. So we're going to set x equals 1. And we have it just sitting up there. It's actually right there. S1 here. And this will be 1 minus S1 here. All right. So this is the result. So the left-hand side is 1 minus S1. And up here we have e to the minus average degree times S1. So, you know, you can't, I mean, it looks like you can't solve this. In fact, you can invert it and write the average degree as a function of S1, as a function of the size of the giant component. So you can actually plot it properly. We have seen this before, but it's come from generating functions. And it crosses at 1. There's a solution along 0 as well, so you can imagine a dot, dot, dot here and a dot, dot, dot here. So that's the crossing. So we got it from generating. This is just for pure random graphs. But the story for how to do it for arbitrary ones is now clear. How are we doing? Yes.
So it's because we're dealing with pure random graphs that we can use that trick. Is it the one which
Pure random graphs allow you, well, pure random graphs is just this. It's this fact. It's this fact.
and equate the
That's all.
FP and FR?
Yep.
Generating.
You just know, you observe that to be true.
Yeah.
Only because of the actual, yep. So only this case. It's only this case. Otherwise you have to solve this equation separately and then plug it into here. Yep. Yep. But that's why it worked before you make this bad mistake, treating them the same way. Because they are the same for this particular thing. All right. Okay, so you can do lots of other things. Average component size is a good thing to find. This is going to be the average component. This is a very nice kind of physical system sort of story. It's the average size of the finite components, right? So the average component size when you're out here, so there's some little guys, right? There's the little components here. This is the fractional size of the largest one. There are some, you know, there's the second biggest one, the third biggest one. As far as an infinite network goes, the largest one is of 0 size. It's tiny. Here it's macroscopic, right? There's a big giant one, and there are little satellite ones. At this point, this is at average degree 4. Most people are in that big component, whatever they are, nodes. But there is some finite. There are all these finite ones, and you can average their size, right? So this has another interesting kind of thing. So, all right, the average of a distribution of a quantity given a different distribution is the first derivative of the generating function evaluated at 1. So that's nice, right? So let's see what we can do with that. Of course, we don't want to find f of pi. That would be horrible. So we can kind of play around with things. So we start with this left-hand equation that we had, right? So the generating function for pi, it's the generating function for the underlying p, which we really know with this guy, composed with this guy. Generating function for rho. So you can differentiate this. So let's see if this is correct. So we're going to take one derivative here. The first, we have an x times all of this, so that's just, right, so product rule. Boom, we just have this guy, comes down. And then x stays, and we're going to differentiate this. And it's a chain rule, all that good stuff that you guys know all about, right? Look at it. Oh my God, it's being used. Okay. Evil but useful. So the insides come out with their derivative, and then it's the derivative of this guy with the insides unchanged. Okay. Yeah? Very chain rule-ish. In the spirit of the chain rule. All right, so that's interesting. So then we have to set this to 1. All right. Now we can take the second equation and mess with that one as well. So maybe you need to look at this. So this is the second one, right? F of rho in terms of f of rho. Right. So we're going to do the same thing. It should look exactly the same, really. So there's a derivative. The x goes away, so that's the first. That's this bit. And then we have our x times the chain rule result. Derivative of r. The f of r, derivative of f of rho at the front. Right. Goody. Goody, goody. Yeah. Okay. So if we put x equals 1 in both equations, right? So that's what we want. Right. So we're going to know a few things already. We know f rho of 1. We know the size of the largest, which is essentially 1 minus s1. So we know that. That is going to be, that's going to appear here. So this will be just some number. This will be just some number. And then we actually have, and this is a 1. So we have this blob and this blob. Right, they're the guys we're trying to get to. So we'll put a 1 here and a 1 here. So it's just a linear thing, right? So we'll put this on the other side if you like, perhaps. And we have this blob here at some number. Divide through. And we'll isolate it by itself. And we'll be able to do the same thing here. Once we've got this guy, in fact, once we've got this guy, we just plug in the result, right? There'll be a 1 here, a 1 here, 1 here. So we know what this number is, we know what this number is, and we have some new expression for this guy. Right? So that's the story. We're going to plug it into the first equation, and we'll get this first derivative evaluated at 1. All right, so let's do standard random graphs. So we've got to always do that just to see how bad it is. Silly it is. And we'll do it like this. Okay, so right, we've already got this result that that things collapse. The generating functions match up, and so we only have one. Because of that, we only have one equation. So we only have one equation to differentiate. Same idea. We're going to rearrange everything. Right. So you can see we've isolated this guy. Okay, so I've put all of this over on this side. And this bit is here, yeah? And there's 1 minus x times all of this. Cool, cool, cool. Okay. We know a little bit about these things. Yeah. This is just for yeah, it's just for this guy, right? So we know for pure random networks we have f of p of x equals e to the minus 1 minus x, right? So the first derivative of the thing is equal to, it's just going to be this guy times itself. Right, we're going to pull down this guy, average degree. This is the same, so we can write it like this. Okay, good. We have even more sneaky things. Okay, so that fixes up this piece. Right, so it's going to be an average degree times f of p. And it'll look like this piece on top. And then we can replace f of p or f of pi using this result. Right, this is the original equation that we've been using so much. And it's only for standard random graphs. We're going to set x equal to 1. And we're going to replace f pi of 1 with 1 minus s1. So lots of steps. Right. And if you do that, we get this blob. Right, so the f of pi of 1 is 1 minus s1. That's going to be here. There's going to be a 1 minus s1 here. We get the average degree appearing here. And 1 minus everything on the bottom because of this. So this is the average size of a finite component. All right. Yeah. So we need to know what S1 is, right? That's that phase transition story. Once we have that, we can put it in. And you can see, though, that things will potentially explode, actually, right? So if you set, let's set S1 equal to 0. Here's an idea, right? So let's set S1 equal to 0. So imagine we're on this side of the phase transition. We're here. So we're going to set S1 equal to 0. And this is average degree. We're going to tune the average degree. So what happens if, so S1 is 0. So this is just 1 minus average degree on the bottom. So what happens? Yeah, well, it's 1. So, yeah, 1 minus 1 over 1 minus average degree. So what happens is this average degree increases from 0. Yeah, so this is the average. So before this plot that I've been showing you has a maximum of 1 because it's the fractional size. It's a fractional size. This is not a fractional size anymore. This is the average component size, right? So it's averaging numbers 0, 1, 2, 3, 4, right? Well, has to be at least 1. 1, 2, 3, 4, 5. So what happens is you get to, right? So S1 is 0, it's going to be 1 over 1 minus average degree. What happens? Yeah, well, so this thing is increased. So when it's 0, it starts at 1. It's always increases, right? And it becomes very large.
See, 1 minus is a very large thing.
Average degree hits 1. It becomes,
Well, the denominator becomes 0.
yes,
So the thing is
explodathon, right? Yeah, right. So it goes kaboosh on a different scale. This is one, this is a fractional thing here for this guy. And in fact, looks like this on the other side as well. So this is the average size of the finite components. This happens always around critical, typically happens around critical transitions in all sorts of systems, right? So something, you're here, yes, the largest one is from a global scale 0, can't see it. But if you look at the average size, it's exploding, right? So it's going to go, and so this is kind of like, this is ice turning into water sort of thing, or the other way, whichever transition you kind of want, or water into gas, right? So, but think of water going into ice, right? So it's not ice yet, but it's getting bigger and bigger pieces, and eventually has to transition. So this is getting bigger and bigger subcomponents, but up until that point, none of them are infinite. You cannot see them, and you have to go out this other side before you see an infinite size one. All of these things are here. For this guy? Oh yeah, so this is coming up from this side, from the left-hand side. Yeah, for the right-hand side, we have to think about things in a slightly different way. But it's going to be, I'm filling this in for you. This will happen in a similar kind of way. Yeah, explodes. All right, so I think everything I've said is in fact here. You actually, right at this transition, you get a power law size distribution of sizes, right? So there's not quite an infinite one. If you get just a little bit above it, you can start to see the biggest guy, right? And then the distribution starts to break, right? So the distribution is spreading out and out and out, and then suddenly it starts to get a little spike, and the rest of it starts to shrink back, and you get one dominant one. Okay, so there's some more stuff here. I think this is okay. I mean, when average degree is infinity and 0, it's may have to fix that up. But it is true that there's this extra piece here. So that This is just for, this is again for pure random networks. S1 is scales as n to the 2/3.
Where capital N is
The
the number of rows.
yeah, that's not right. It should be n to the 2/3 divided by n. Right? This is a fractional size. Right. I mean, if you have the absolute size, then it grows like that. Above it, it's some fraction of n. It's some explicit fraction of n. Yeah, I'll fix up that notation. Okay, so that's enough.